Okay, so CU Prime talks are not your typical physics department type research talks. The goal isn't necessarily to describe any part of my research particularly well. The goal is to hopefully humanize me as a scientist and researcher and give you all an idea of what it looks like to go to graduate school and maybe do the type of research that I do. That being said, along the way, if I say anything that's confusing or sounds wrong or you want to know more about, stop me and say that's confusing, wrong, and I want to know more about it. And we can talk about it in some of that. Okay, cool. So here's a brief outline of my talk. First, I'm just going to go over a little introduction of who I am, what I like to do, and where I came from. Then I'll briefly go into a little background behind my work, so the intro to magnetism section. I'll talk about what it's like to do an experiment in condensed matter physics. That's the area of physics I work in. We'll talk about what that means along the way. And then I'll give you a look at what it looks like as a graduate student from kind of day to day. So who am I? Hello. My name's Ian. I start with this slide because I want to humanize myself. I'm not some person in a lab coat that's doing science that you've never seen anywhere before. I like to do fun things. I like to hike mountains and climb rocks and all this kind of stuff. So actually, this picture in the middle of me wearing that orange coat, that is my first 14er that I just did a couple of weeks ago, actually. If you're new to Colorado or aren't in Colorado, 14er is a mountain that's over 14,000 feet. This one is like 14,005 feet or something. So it's the easiest of the 14ers you can do, but it's a blast. I really like hiking. This picture in the top corner is of me rock climbing, ice climbing if it's a day like today, playing music if I can't go outside. And yeah, this is a picture of an upcoming album cover that I have. And I want to show all these things because it's really important, if whatever you're studying, whatever your work is, to your time is what you have, right? You want to make sure you're taking care of yourself. And especially I've found that physics is like a hard thing to study. And it's definitely good to have ways to escape that and really center yourself so you can come back to your work stronger if you want, and so you don't lose your mind. It's important to have hobbies, I think. Anyway, okay, so where did I come from? I'm originally from Pennsylvania. So this star roughly corresponds to where I'm from. I'm from a little town called Mahanoy City. So this is a picture of the main street. And if you look too far to the left or too far to the right, the buildings are all decrepit and fallen down. It's an old coal mining town. Its claim to fame is that we invented cable television. I think that's real, but that's what I've always believed. And my high school mascot was the golden bear. And I bring up my high school because that's where I first found out that I even cared about physics. I was good at math and I was good at science in high school. And I thought oh, maybe I'll be an engineer because that's what I had heard people do if you're good at math and science. And I had a physics teacher who realized that I really was curious about the world and really curious about physics in particular. And they really cultivated in me a sense of wonder around physics and really inspired me to go to undergraduate for physics. I had opportunities to teach my peers in high school and maybe build a small experiment or something. And that was awesome. That was really a life-changing circumstance. So I think his kindness definitely inspired me to pursue physics further, which is awesome. So yeah, from there I went to school not super far away in Villanova. It's right outside of Philadelphia. We're good at basketball. If you like college basketball, that's what Villanova is known for. I got my bachelor's in physics in 2014, and I minored in math because I still and continue to really like math. Just so you could see what 4 years of a physics undergrad does to somebody, this picture is of me on my first day, and I'll try to circle my head. This is me on my first day, and this is me on my last day. So just as a rough idea of what the physics program did to me. No, I'm kidding. I had a great time learning physics at my department. It was really small. It was close-knit. Yeah, it was wonderful. At Villanova, I really liked hosting a radio show. Music has always been really important to me, and I got to host a radio show at Villanova, which is really fun. I get to broadcast music that I like over the airwaves. And it's also where I got introduced to undergraduate research or research in general. So until then, I thought physics was just about like, you know, you study something, like you read a book and you learn about it, or you do a problem and that's it. But that's not it. My undergraduate research experience was in condensed matter physics, which is what I'm still doing now. But condensed matter just means like a solid. That it's an apt name, condensed matter. Yeah, so the solids I were working on look like this. So this is a crystal structure. It's just some arrangement of atoms from the periodic table. It doesn't matter what colors are what here. The important thing to note is that I was working on combining strontium, calcium, iron, and cobalt with oxygen together in different ways to form different crystal structures. And what it looks like was I'd grind up some different powders of these elements, and then I'd bake them in expensive easy bake ovens. And then this thing on the bottom right here is a X-ray diffractometer. So it shoots X-rays at crystals, and the X-rays scatter in a certain way depending on how the atoms are arranged. And from that information, you get a pattern that kind of looks like this. And these peak locations can be used to tell you where atoms are in a material, which is really cool. What I was trying to study was how these peak locations, or how the crystal structure of something changed when I changed the elements that were in it. So that was really cool. I really liked that research. Also, during my time in undergrad, I got a chance to experience research outside of just a small lab. So Triumph is a facility in Vancouver, Canada, and it's known for, at least in the condensed matter physics community, as a place to scatter muons, the particles. So basically you shoot muons into some material and then they spin around and then they eject. And from how they eject, you can tell information about the magnetic structure of the material. We'll talk about that in a bit. So I got the opportunity, thanks to my undergraduate advisor, to go like do some research at this experiment. It was awesome to see like, oh yeah, like people do that as a job. Like you could like get a job doing research like at a national lab. Like that's a thing that exists. Like our society values science, so they fund things like this, which is cool. Yeah, okay. So then after my time at Villanova, I moved to CU Boulder, where I am now. I decided to come here. If any of you are going to make a decision on going to graduate school someday, make sure you make the decision that makes you the happiest. That's the decision I made. Yeah, so I visited a bunch of different places. This one seemed the happiest. It had the best tap water, and the people were the friendliest. So I came here. I figured that I could spend the most time being the most happy in this place. So that's where I came. Yeah. And in case you've never been to Pennsylvania, the difference in geography is severe, and weather. So it's like a big change in almost every way from Pennsylvania. Okay, so what have I been doing at CU? Well, that leads me into my Intro to Magnetism section. So my lab looks at the properties of magnetic materials, as well as how applied magnetic fields can change those material properties. But like, what does that even, that's like pretty vague, and what does that even mean? Don't we know everything about magnetism? What's left to learn? Great questions. I mean, we use like fridge magnets to stick our like postcards and I don't know, coupons to the fridge. We use magnets to store data on our hard drives. We use magnets to convert our voice to a louder voice. So like, I think we have magnets pretty figured out. Like, what's left to figure out? Okay, which leads me to my first discussion question. So if you're new to CU Prime Talks, the way discussion questions work, we will break you all out into small breakout rooms of about 3 people. And we'd like you to discuss this question in those groups, and then we'll come back together and we'll all talk about it together. So it's hopefully, if you meet somebody new in this process. So when you get into the room, make sure to introduce yourself, say hello, say who you are, say if you're liking the talk so far or not. No, I'm kidding. And then start talking about the discussion question. So I'll read the discussion question. What do you know about magnets? If a material behaves like a magnet, does it always behave like a magnet? That's an important question. Is there only one type of magnetism? So what do I even mean by that? And can any material be magnetic? Yeah. There we go. I couldn't see anybody. Okay. Before I start sharing my screen again, what did everybody talk about?
we got as far as agreeing that if you got all the electrons spinning in the same direction, at least if the vectors are all the same, then the material acts like a magnet. And conversely, if they're all at random, then it probably doesn't act like a magnet. At that point, we ran out of time.
Oh, I see. So I cut you off too quickly, huh?
A little bit. We got introductions.
Okay, good to know. This is our first virtual CU Prime talk. So there's another discussion question. You'll have time to meet some new people, and I'll definitely give you some more time. Yeah, so it sounds like you talked about the flowing of charge is like, if charge flows a certain way, it can create a magnetic field. Is that what you talked about? Anybody else?
I'm still taking physics too, but what I tried to do was I tried to make an inference about how magnets would work just reading off of Maxwell's equation, telling you that the divergence of the magnetic field is 0. So what that tells you essentially is that the entire magnitude of it is going to be perpendicular, and also that it's not going to go out radially. It's not going to have vectors that are moving away from some point like the electric field does. So there's not going to be an inverse square law. Instead, you're going to have some sort of curl where the magnetic field is moving about some point, and yes, there's just not going to be an inverse square law. That's
Awesome.
how it behaves differently from the electric field.
Yeah, that's really important. So like most of the like macroscopic magnets that most of us have ever seen will like interact in a way that goes like not 1 over r squared, like you had said, but 1 over r cubed. Yeah, that's a good point. Yeah. And maybe one more. Oh, I see in the chat, diamagnetic versus paramagnetic. That's exactly where I'm going with it in a minute. Any others?
Like pretty much me and the rest of my group, we didn't really have any sort of, we didn't really know anything about magnets. Well, I know like at a basic level, like magnets are responsible for repulsion and attraction, like magnetism. But I think also, I think I heard this like a YouTube video on Richard Feynman that there's like magnetism at basically, well, everything sort of has a magnetic field. I don't know if that's true or not, but I don't know. Yeah, I pretty much like we didn't really know anything about magnets.
That's right. It sounds like you do know stuff about magnets. Yeah, those. Yeah. So I think you might be getting at like everything is magnetic, which I'll talk about in a little bit. Yeah. Magnets are attracted sometimes and repulsed sometimes. That's definitely something. Also, I think you touched on a little bit. It's sort of similar to like gravity in that it's sort of like one of those, I'm going to air quotes, spooky action at a distance forces, right? They don't have to be touching for them to exert force on one another. Yeah. And then, okay, Leonardo, you had your hand up, so you should get to talk. You should remember, raise your hand.
Yeah, no, we just talked like about the different types of magnets and how it was something that I didn't know, but my colleague said that basically anything can be turned magnetic. Like for example, the frog at the beginning of the that was like suspended because of magnetic fields. And then we also mentioned that I read this somewhere. There's like a temperature where materials kind of lose or change their magnetic properties.
Mm-hmm.
And so we just touched a bit on that. Yeah.
Awesome. Cool. Okay, Hannah, I see you have your hand raised. The last one.
So this is like kind of also related to like the fact that you do condensed matter, but I was also thinking about like flux tubes, like related to the question of can like stuff behave as a magnet, right? Because it's like some condensed matter systems have like these quasi particles, right? And they're like mathematically analogous to magnetic monopoles. So they behave like it, right? But they aren't actually
yeah,
the magnetic monopole.
Yeah. Yeah, so that's like a different type of magnet. That's a highly sought after. that goes with Lachlan's comment about Maxwell's equations, right? Like classical electrodynamics says you can't have magnetic monopoles. So in condensed matter system, if you have some evidence of what you think is a magnetic monopole, that looks really cool because it would break some part of physics in a way that we don't understand. Yeah, cool. Okay, so those are all great answers. Hopefully you can see my screen again, but only the slide. I'm trying to monitor the chat and the participants at the same time, but if I miss stuff, I'm sorry. I think if you use the raise hand feature, if there's questions, that's the best. Okay, so all materials exhibit some sort of magnetism, but not all forms of magnetism are the same. So ferromagnetism is the one that we're all probably most familiar with. That's the thing that makes your fridge magnets work, or the magnet in like a speaker, or what have you. So electrons have a property called spin, and you'll learn more about what that is eventually. But we can picture it acting like a little bar magnet. And those little bar magnets are on every electron that's in any material. In ferromagnets, all those tiny bar magnets, all the electrons bar magnets point in the same direction. That's what makes it ferromagnetic. In different materials, the thing that makes these bar magnets weird, the electrons bar magnets, is that they don't have to follow the rules you think they would. They don't necessarily behave like macroscopic bar magnets do. Depending on the material, they can interact in different ways with one another. And that leads you to all kinds of things. So not all materials are ferromagnetic. You can't go up to a fridge and stick any material you want on it. But all materials are diamagnetic in some amount. It's usually just really small. So this is a picture I used to hook you and get you in here. This is a frog floating in a solenoid, which is a device we use to make a magnetic field. And we need a pretty big field to levitate this frog, like I think 6 orders of magnitude bigger than the Earth's magnetic field, so pretty big. Yeah, so this frog is floating around because it's diamagnetic. It has a diamagnetic response. What diamagnetic means is that when you apply a magnetic field to the frog, it generates, it makes a bar magnet out of the frog, but the bar magnet is facing the opposite direction, right? And if you've ever brought 2 bar magnets close to one another, but had the opposite poles, like north and north together, they don't want to go together, right? They repel. And that's what's happening to the frog. Except every time the frog rotates, so does the orientation of the frog's induced bar magnet. Hang on, I saw something in the chat. I thought it was drowning. Yeah, it kind of looks like it's in an eyeball in the picture on the poster. Yeah, okay. So we have ferromagnetism, diamagnetism. We also have a type of magnetism called paramagnetism. This is like diamagnetism, except instead of inducing a bar magnet that's opposite the direction of the applied magnetic field, it's a bar magnet in the applied direction, field direction. So if you've ever gone and picked up a paperclip with a magnet, you can think about this roughly as being like a paramagnetic thing. The magnet comes close to the paperclip, makes the paperclip look like a magnet, and then they attract. Yeah. But this isn't all there is. Right, so I said a minute ago that we can picture ferromagnetic materials being made of a bunch of atoms that have a bunch of electrons that all have tiny bar magnets that line up in the same direction. So zooming in on a ferromagnet, these electron spins, or bar magnets, would look this way, right? So they'd all be pointing the same direction. The rule in a ferromagnet is that that's the case. That's not always the rule. There's some materials that are what are called anti-ferromagnets, which is exactly not ferromagnetic. So if you look at these, all these bar magnets or electron spins are pointing opposite directions from one another. So there's a set of, if I pick any one here, like let me highlight one. If I look at this one, all of its neighbors are pointing the opposite direction. So this is an anti-ferromagnet. We're also not limited to just ferromagnets and anti-ferromagnets. Depending on how we arrange these bar magnets relative to one another in space, we can get strange geometrical effects as well. So I call this one a honeycomb magnet because it's shaped like a honeycomb. The blue arrows are these bar magnets, the electron spins, and they lie on these spots that form a honeycomb if you trace out lines in between them all. And they interact in a certain way. If you look, it's actually not like they're laying in flat in the plane. It's like a 3D thing, right? They're all tilted up in a weird kind of way. And you might imagine that this might have some effect on a material's properties, and spoiler alert, it does. And we'll see that later. But it's not always even clear cut like how a system is, how these like electron spins or bar magnets are organized. Take for example, let's say we had an anti-ferromagnetic rule. So all of the spins or all of the bar magnets in our system want to anti-align. So if my lattice was a square, and I look at this first thing, okay, I put one down. And then it's easy to look at my neighbors and go opposite those directions. And same thing here, right? But if instead my lattice was a triangle, I can make put one of my bar magnets down, make this one opposite the direction, but then the third one has no well-defined direction, right? If you put it upwards, you're making this bar magnet unhappy. If you put it downwards, you're making this bar magnet unhappy. So there's no right answer. This is called the geometrically frustrated system, and that can lead to lots of interesting measurable properties, which is neat, including magnetic monopoles, like we talked about a little bit. This also is not the case. So we can also observe these things called interesting magnetic spin textures. So this is just an arrangement of these bar magnets that looks pretty strange. So this one's like a helix, so it's called a helical magnet. This one is technically what's called a quasi-particle, or a skyrmion quasi-particle in this case, but it's really just this strange arrangement of the electron spins, or the bar magnets in space. So all of these different types of interactions exist, and I'm just listing like 5 that I thought were cool here. There are hundreds. There are so many, and all of them generate unique properties in materials that we can measure. So how do we research these novel magnetic materials? And I'm calling them novel magnetic materials because oftentimes the materials I get to study haven't been researched before. They haven't been looked at. So for the first time, I get to like look at a material, measure it, and tell the world why it's interesting, which is awesome, and what's called novel. So I'm not interested in like how these things will necessarily be applied, but I'm interested in understanding the physics that makes them the way they are. Yeah, so how do we research these things? So what is useful to measure if we aren't sure how a novel magnetic material behaves? As a hint, think about water and ice. What are some ways we can quantify the difference between these phases of H2O, right? So what are some things that you could measure that would tell you if it's water or ice, liquid or solid? And what properties might set magnetic materials apart from one another? So is there anything we could measure that would, directly be able to tell us about the magnetism in the material, like which way these bar magnets are pointing? Okay, so that brings me to my next discussion question, which is, you're working as a research scientist, and you're given an unknown material to study. What are some properties you could measure, and why would you measure those properties? So if you're trying to figure out what some hunk of stuff is, what could you measure to tell you what it is? Why? And are there any properties that are specific to magnetic materials that might be useful? So I will paste the question in the chat again. Okay. And I will break you all out again, and we'll come back together in longer than the last amount of time to have a chat. Okay, I've given this talk 2 times already, and every time I think somebody's come up with the idea that I'm looking for, like, first off. So no pressure, but no, I'm kidding. What did you all think about in your breakout rooms? Don't forget, raise your hand first, please. Oh, Doug. Okay.
Yeah, in our group, Ingrid was playing around with the idea of it's important to know what the crystalline structure is. And I wasn't really sure whether we talked about density at one point, but I wasn't sure. I raised the question as to whether a real dense structure, dense is a lot of mass per volume, still has the same number of atoms. So if you shoot X-rays into it, you get kind of the same results. And
yeah, that's a good question. Yeah, that does totally happen. So different atoms absorb X-rays in a different way. So sometimes it's easy or hard to see where the atoms are depending on how many like protons and neutrons they have. So for example, with X-ray scattering, it's really hard to see like a light atom like carbon or oxygen, but it's really easy to see heavy atoms like, I don't know, iridium or ruthenium or some heavy atom like that. Yeah. Hassan.
Oh yeah, like our group. So like we said that you could basically like you could measure the amount of protons, neutrons, electrons, um, and we just started talking about other like basically like chemical properties. We also mentioned boiling point and things like that, and we just we also mentioned the physical texture of the substance and like elasticity and things like that.
Yeah.
Yeah.
Cool. So it sounds like different mechanical properties, maybe like how it stretches, like when it breaks. Yeah, those are super useful. Michael.
I guess one idea that I had was like, certain materials have natural magnetism, and certain materials you can like give it magnetism, but you can also like take it away at certain temperatures. So you could like gradually test the magnetism of this unknown material at, certainly raising or lowering the temperature, and like seeing where that loses or, whatnot. It's magnet integrity and just like loses it altogether, and you could lean more towards this material and whatnot.
Yeah, that's awesome. That's the answer I'm looking. No, I'm kidding. Yeah, so that temperature is called the magnetic ordering temperature, where a system goes from all of those bar magnets doing whatever they want to all following the rules and facing a certain direction or what have you. Yeah, so definitely studying some property, be it how magnetic it is, but as a function of something else, like temperature, is something that we definitely do. Yeah, great answer. Maybe we have time for one more if somebody else wants to. If not, that's okay too. I'll just start sharing my screen. Okay. Okay, yeah, great job. All those ones are definitely things that we measure. We might not measure the density like per se, but if you measure the crystal structure, you can figure out the density. Okay, here's a list of all the things we measure. The important thing is not this list of names. Those are just the different techniques we use to measure these things. But the important part is the words underneath the pictures. So magnetization. Magnetization is a measurement of how magnetic something is. So how strong of a magnetic field does something produce? So ferromagnets produce strong magnetic fields. Antiferromagnets should produce weak magnetic fields, right? Yeah. So these are just different techniques we can use to measure this magnetization. And usually when we're measuring the magnetization, we study it as a function of changing temperature, like Michael said, or changing magnetic field. So you can apply a magnetic field and change the magnetization also. So both those seem like good levers to pull on to control what's going on in the experiment or change it in some way. Yeah. We also measure crystal structures, like Doug had brought up. Yeah, so those are usually what are called diffraction experiments. So usually what we do is take X-rays or neutrons or something, and we shoot it at our crystal or our powdered version of a crystal, and they'll scatter in a certain way. And based on the way they scatter, we can back out information about how the atoms that make up that thing are arranged in space, which is super cool. We study this often as a function of temperature too, because sometimes things can have what are called structural phase transitions. Their structure can change as a function of temperature. Yeah. We also measure electrical conduction. So electrical conduction, it's a measure of how well something conducts electricity. So oftentimes we're looking at some piece of material, and electrical conduction is a good thing to measure. So in this picture, I have labeled battery, an applied current, and R. R is the resistance of some material, right? And materials can be more metallic or more insulating, or kind of a mix of both or whatever. But measuring the resistance can tell you about that. And sometimes the magnetic structure in a material can interact with the things that are carrying charge in the material, like electrons. And you can see that, which is cool. So you can use that to make guesses about what you think is going on in the material. Just as a quick note, resistance is something that's dependent on geometry. Resistivity is really the thing that we care about. Resistivity should be the thing that's like generic between different like size samples of the same material, right? If you account for geometry correctly, but resistance is not, has geometry information in there. And lastly, we measure heat conduction. And I showed this picture of a pizza because of a great analogy or a great story I had to describe the heat capacity from an undergrad professor, which I need to honor. So how come you can put pizza in the toaster oven and take it out by the foil and that doesn't burn you, but then you put the pizza in your mouth and it scalds you? Well, it's because of the heat capacity of those things, right? And their thermal conductivities. How they conduct heat is why they don't burn you, or why the pizza will burn you and the foil won't. And how magnetic materials can conduct heat is an interesting property to measure. Oftentimes, we can see maybe when the temperature when the material goes from not a magnet to a magnet, it'll have a difference in how it conducts heat, which is pretty cool and a cool way to look for what we call magnetic ordering in materials. So next, I'm going to just bring you through a brief overview of what it looks like to do an experiment. So the experiment life cycle in a condensed matter lab like mine. So step one, what material do you want to measure and how do you obtain it, right? So you have to have an idea of like what you want to look at. And usually that looks like going on some websites with papers on them and reading what's been done, like having an idea of what you think is interesting, what physical phenomena you think is interesting. Maybe you think this property called, I don't know, magnetoresistance is interesting, and you want to make a material with the largest magnetoresistance. Well, how do you do that? You have to do some research first about like what materials have really large magnetoresistances, and then try to do something based off what you think is happening. Yeah. So once you have an idea of the material you actually want to measure, you have to figure out how to get it because it might not exist. And this happens frequently. When materials don't exist for us, we end up either asking our collaborators to make them for us, or we make them ourselves. So we do this process called single crystal synthesis. And single crystal synthesis, what we want to do is make a piece of material that's called a single crystal. And we want a single crystal because we want to be able to probe properties of a material in different directions in that material. And single crystals allow us to control what direction we measure properties along, which can give us a more complete picture of the physics governing that material. So we talked a little bit about a crystal structure earlier, but if something is a single crystal, it basically means you have some atom on the very end of the material, and then in your head, you have the rules that make up the crystal structure of that material. And if you follow those rules, you should be able to get to the other end of the material without any disorder, without any like interruptions. It should all just fall into place relative to one another based on those rules. That's a single crystal. So we can imagine that if we had a bunch of atoms that were really close together in one direction, but really far apart in another direction, that material might conduct heat and electricity in different ways in those different directions. And it's important to measure both of those to get a more complete picture of what's going on in any given material. So the way we do this is with a process called chemical vapor transport. And it's sort of like growing rock candy. So if you've ever made rock candy, you dissolve a bunch of sugar in water and you make the water hot so you can dissolve way more sugar than it normally can hold. You super saturate water with sugar, right? And then you get a string and you dip it in some sugar. You should do this if you haven't. And those are called seed crystals. And you put it you hang it in the sugar solution and you wait. And you'll nucleate the single crystals on the piece of string, like these big rocks. So we do sort of that, except it's a little different. We don't care about sugar, we care about different raw elements. So this picture I have here is called a glove box, and inside of it are a bunch of raw elements. So they're in these little vials and containers all over the place. And they're literally just like things from the periodic table. We'll have like a container of sulfur, a container of iron, a container of like nickel or something. And with those, we can think of the material we want, mix them together in the proper way, fill them up in a tube. So instead of a glass of water, we use a tube with iodine gas in it. Yeah, and then we put that tube with our material inside of another very hot, glowing red hot tube to cook for a long time, just like another easy bake oven, but like kind of fancy. Yeah, so instead of sugar coming on and sitting on the string, our material moves down the length of this sealed tube and grows on the other side. So that's how we grow our single crystals. okay, so once we have the material, once we've obtained it, either by growth or asking somebody to help us grow it, what do we even measure? What's interesting to measure? Do we expect any interesting behavior in the material properties? Where and why? So I mentioned that two of the main variables we control are temperature and applied magnetic field. So that's what I mean about the question there, where do we measure? So like if a material has a magnetic ordering, but it happens at, I don't know, like 100 degrees below room temperature, then it's maybe not worth it to measure at room temperature, right? Maybe you get close to the region where something interesting might happen. So it's good to have an idea of where you want to do your experiment and what you think might be interesting to measure. If a material is an insulator, meaning that it doesn't conduct electricity, then it's really hard to measure its resistance. So maybe that's not an experiment that you want to do. Maybe it wouldn't tell you anything. The next step is to plan, measure, revise, and repeat. And I just want to take a second to say this is a highly not linear process. It's not like step 1 goes through step 5 and then you just go back to the beginning. Oftentimes there is lots of swapping in between all of these steps. This is just roughly what it looks like. Yeah, so you plan your measurement, you perform your measurement, you look at what that data has said and tells you, decide if you need more or maybe wish that you had less, and then you repeat the experiment. Either with a different material to give you more information or maybe in a different direction or something like that. Yeah, so, okay, let's give you an overview of what a measurement could look like. So let's say I wanted to measure the resistivity of some material. So Ohm's law says that voltage equals IR. And if you haven't taken physics 2 yet, that's okay. Voltage is like what comes off of the battery and I is just the flow of charge. R is how averse to the flow of charge some material is. So, okay, here's my material. This rectangle in white is my sample. It's labeled sample. The ovals on the ends are current. So basically, I hook up wires to those ovals on the end, and that's how I flow my charge through the material. And then the circles in the middle are where I measure my voltages. So I flow my charge. I know how much charge I'm flowing. I measure a voltage and measure how good of a battery the thing is in response to the applied current. And then with the division of those two quantities, I can calculate the resistance. And oftentimes you might think like, oh, a measurement is way more complicated than you're schematically saying it is, but it's really not. Like, okay, this is a real experimental setup. The width of this sample here is about 1 millimeter or so. So keep in mind that that's pretty tiny and needs to be done under a microscope. We can talk more about that later. So this is about 1 millimeter wide and maybe 3 or 4 millimeters long. And you can see these little, let me get my pen, just a second. There we go. These little gold lines, those are little wires made of gold. They're thinner than a human hair. Yeah, and they get bent into place, touch the sample, and then we glue them down with some metal glue, basically. It's made of silver. Yeah, and then if you follow those gold wires back to these little spots, those go up out away from this material and into our instruments, so we can actually do the measurements. We can hook it up to something to supply current. Usually, I said we like to control temperature and control magnetic field. If you've ever, like, I don't know, taken something out of the freezer and set it on the counter on a humid day, it gets covered in frost. That's not, like, it makes it taste funny. Also, if you put it back in the freezer, you can imagine that if our samples get covered in frost, they might break. They're very delicate. So often what we do is put our samples on a thing called a probe. So this is a probe that I've recently built. Our samples go on the bottom of this probe here. And the bottom of this probe is capable of reaching 2 Kelvin. So that's pretty cold. Outer space is about that temperature. Yeah, which is awesome. We get to do experiments at 2 Kelvin. Yeah, so we put our sample somewhere down here at the bottom of this probe, and then we'd run wires up to the top of the probe where it's not 2 Kelvin to keep the 2 Kelvin stuff really far away from our measurement, to isolate it so it can stay that cold for long periods of time. Yeah, so we put our experiment on a probe, and then we load this probe into something called a cryostat. And the cryostat is the tool that we use to control magnetic field and temperature. So cryo temperature, cold things. So we fill the cryostat with cryogens, namely liquid helium. So helium has a boiling point of around 4 Kelvin. So that's 2 degrees warmer than outer space. Far below room temperature in Fahrenheit or Celsius. Yeah. Yeah, so this machine has a hole in the top. We just stick our probe in it, and we can control temperature, usually between 2 Kelvin and 400 Kelvin. and we can control magnetic field from 0 Tesla to 14 Tesla. And I'll give you an idea of how big that scale is in a second. So usually when we're applying, just so you have an idea of the orientations of these things, when we're applying a magnetic field, the field comes out or through the sample. So that's what this circle means down here in the bottom left. Okay, so just as a sense of scale, 0 Tesla on the left, the Earth's magnetic field is 50 microtesla, micro being 10 to the -6 Tesla. The typical fridge magnet is on the order of 1 to 10 millitesla, so much bigger than the Earth's magnetic field, but still seems pretty tiny. It's got milli in front of it. That one magnet that you played with that one time was really strong. It's probably like 0.2 to 0.4 Tesla. Speakers usually have a magnet that can be up to a Tesla in them, and most people, if they've experienced a field larger than this, will probably be with an MRI machine, which is on the scale of 1 to 3 Tesla, but can, I think, now go up to 7 or something. For our experiments, we use 14 Tesla here at CU Boulder, and sometimes we even get up to fields of 65 Tesla, but to do that, we have to go to a national laboratory. Which brings me to here. So measurements at national facilities are a thing that we definitely need to do. So at Boulder, we have access to applied fields up to 14 Tesla, but what if we want something larger? And that's so very frequently the case. You see some interesting property that gets very interesting right at the limit of your experiment, and then you want to apply and study it at a higher magnetic field. So to get higher magnetic fields, we go to national laboratories, which are facilities that host scientists from industry and like research institutions to go and do experiments. They get to maintain all the equipment, and you get to use all the equipment, which is awesome. So your experiment's like much more hassle-free than normal. Yeah, so if you want a field that stays on as a function of time, so you could like go to some set field and sit there for a long period of time, you want to sit in a DC field. And you go to Tallahassee, Florida, the humid Tallahassee, Florida for that. You can get up to 45 Tesla, I think, there. If you want to sit at a really much bigger field, like up to 200 or 300 Tesla, but for a much shorter period of time, like milliseconds, you go to a pulse field facility in Los Alamos, New Mexico. Yeah. So what does an experiment look like at one of these national labs? Usually it looks like preparing a bunch of tiny samples. So, okay, here's a picture of, there's actually 8 samples here. There's only 4 that you can see, but there's 4 on the other sides of these like platforms. So that takes a while because it's really tiny and under a microscope. Yeah, so you prepare your samples, and then once your samples are prepared, you stand on the stage above the cryostats that they have. This is cryostat, and you lower your samples into the cryostat on a probe. So the probes there are much bigger than the probe I showed you. The one I showed you before was about a meter long. This one is several meters long. It's like 3 or 4 of me tall. So yeah, there's a stick getting lowered down into the cryostat. And then once your experiment is cold, as we call it, or lowered into the cryostat, you basically just, here's a picture of my lab mate falling asleep, watching the experiment, watching the data come in, taking a rest, which is very, very much needed when you have magnet time. Yeah. So remember that was only like one type of measurement I just talked about. There's all those other types of measurements that we brought up after that discussion question. And we use all those as different tools to get an idea of what we're looking at. There's a really good analogy about like trying to figure out like that some animal is an elephant, but only by touching it and with your eyes closed in different parts. You need to do it a bunch of different ways, right, to figure out what the thing is. We need to do a bunch of different measurements to figure out what's going on in the materials. So just as an example, we measure the thermal conductivity, how well something conducts heat, the Seebeck effect, which is really cool, but I think I'm running out of time, so I don't have a lot of time to talk about it. I'll stick around after if you'd like to hear about it more. We measure magnetometry or magnetization, like I mentioned before. This is like a magnetic sample right here is glued to a little diving board, and then you apply a magnetic field and the diving board bends. And you can measure how much it bends, and it's directly proportional to how magnetic the material is, which is really cool. A lot of our measurements are exactly what you'd expect to do, which is awesome. Yeah. And then diffraction, studying the crystal structure as well. So all these different types of measurements that we do as a function of different temperatures and fields, and repeat this process of going to national labs to do them and back and forth until we build a complete picture of what's going on. So the next step is to analyze data and try to understand the system and hopefully publish. And that inevitably leads to further exploration. You end with some new hypothesis about how some class of materials might work, and you want to test that in some way. Or maybe you say, I'm not interested in these things anymore. I figured them out, and you move on and you find something new to study. Yeah, so usually the experimental life cycle ends in further exploration, not like you finished. Okay, and last, life as a graduate student. So what does it look like to be a graduate student? Well, it's usually split between one of three modes, I think. So the first mode is kind of boring. I don't have any pictures because it's literally just me like staring at a computer and trying to read papers and figuring out what people are saying. So reviewing literature is what we call that, reading papers that people publish in the field that you're working in. The second major mode is preparing or performing measurements. I mentioned before that our measurements are pretty tiny. So here's an actual scale bar. This is a measurement of the thermal conductivity and the Seebeck effect. These rectangles that are on the samples, so this gray bar behind everything is the sample. This rectangle is one of our thermometers. And you can see that on the rectangle, there are two patches of like silver. There are wires glued in those particular spots. And the silver can't go any further or else the measurement won't work. This is an infuriating process to get good at and perfect. And it takes a long time to prepare samples. So sample preparation is definitely something that takes a lot of my time. I had to show this as my like pride and joy as working at a microscope. These samples are less than 0.5 millimeter long, and we were able to glue down 6 wires with just a microscope in our hands to these samples, which is pretty cool. It's hard. You should try it sometime. Yeah. Also, preparing and performing measurements involves doing things like building new measurements or building new tools to help us do measurements. So here's a picture of the probe that we saw before, but I built this kind of recently because I wanted to extend our field range to 14 Tesla in a new cryostat at CU. So we needed a way to put our measurements into that. So I built this probe to do that. So I get to do some machining and like wiring and soldering and stuff, which is pretty fun. Also, a lot of my time is spent in MATLAB, just like writing code to take our measurements and analyze our data. And then a lot of time spent trying to make sure I've hooked up all my wires correctly in the way that I trust myself, and then troubleshooting instruments to make sure they're working together well with one another. The third main mode is analyzing data and writing papers. So once you've set up the experiments, you've collected the data, you read more papers, you try to figure out if anybody has something similar to you, and if not, you get to publish a really nice paper. Hopefully at the end of the day. That involves a lot of MATLAB, and hopefully you get some results, which is the end goal. Hopefully you can contribute to science in some way. Yeah. Okay, so I'd like to thank my advisor, Dr. Minye Lee, my former lab mate, Dr. Peter Siegfried, and my current lab mate, Chris Pox, as well as the National High Magnetic Field Laboratory, CU and CU Prime. And I'd like to also acknowledge that high school teacher who influenced me to keep studying physics, and my wonderful, the wonderful group of people who supported me through my undergraduate studies. Yeah, so are there any questions?
Yeah, sorry. I don't want to sound like a materialist, but do you do you make any money with the graduate research?
Not a lot of money. No, that's a great question. So as a graduate researcher, as a graduate student in physics, you get paid a stipend. So I currently am teaching Physics 1400, so that's how I get paid. Yeah, but it's not like a high wage position. If that's, yeah. And when you're applying to graduate school, you can see what different graduate schools offer as stipends before you go there to see how it stacks up with cost of living in the area and stuff. Yeah.
I was just asking. That's not my goal. But...
No worries. Good question. I saw Shannon next, I think.
Yeah. So when you're working with the national laboratories, do you actually have to go to that place? And if so, do you get to see other research and get to, I don't know.
Yeah, great question. Yeah, so yes, oftentimes we do have to go to those places. I think actually right now they have a program where if your measurement isn't too complicated, if it doesn't require a lot of preparation, you can ship them a sample and they'll measure it for you. But this is new. This is a new development thanks to the coronavirus. So normally, yeah, we have to fly there and we're there for about 10 days. Usually get about a week of magnet time. So you have to sandwich that with preparation time. Yeah, so you definitely get the experience of working with other scientists, both at the national lab that work there as research scientists and people who are visiting doing other experiments. So it's like a place where you definitely get to learn like different tips that you would never think to learn anywhere else, because it's like a group of like 30 people that are like care about the thing you care about and have worked on it extensively. So you all have your own like little tips and techniques that you get to share with one another. So yeah, you definitely get to collaborate a lot at the national labs when you go there. Yeah. Good question.
Thanks.
Evan?
Yeah, so one question I had. So for those of us looking to get into grad school, what would you say is the single biggest piece of advice that you would have for us trying to get in?
I think, I don't know what the best advice is for trying to get in. Maybe just like, don't freak yourself out too much at any step of the way. Like, make sure you have your like GPA is like good. Like, if the GREs are still a thing, like make sure you study for them like early enough so you're not stressing yourself out. And I think the advice that I have surrounding grad school is like you're spending 4 to 7 years of your life there. That's like a lot of your life. Like, make sure you're happy, like whatever you're doing. Yeah, make sure that you like take advantage of the visiting times if you can, and like go visit the places and make sure that you could like see yourself being happy in that place for an extended period of time. I think that's really important. But other than like preparing and being diligent in your studies, I think, yeah, I think that's the biggest piece of advice I'd give. Hannah?
How much leeway do you have to explore like other niches of physics? Because like what I've kind of heard is like once you hit grad school, you know, you have to pick like a specific topic and then, you know, run with it for the next however long. But how much commitment is there in that? And like, should we really be trying in our undergraduate years like to find, you know, our niche in physics?
Good question. Yeah. So yeah, a graduate degree is a PhD in physics is like what's called a research degree. And as part of that, it's like you're supposed to like publish a thesis, which is like a collective like body of work on like a single type of idea, usually in physics. So like, for example, I think plasma physics is cool, but I'm studying like condensed matter physics. So like I wouldn't have much room or like resource right now where I am in my degree to like study plasma physics other than like reading papers on my own or something. Like I don't have any ability to like try and experiment in plasma physics. But during your first couple years in graduate school is like the time where you, I think, really get a sense of like what it is that you'd actually like to do research wise. So like, I'm sure you have a bunch of ideas that you think are cool in like physics that are like open research. So I would say like your first like year or two of graduate school is a good time to like try out different labs and see like what they do and see whether or not you'd be a good fit. That's very important. And by good fit, I mean like whether or not you can like collaborate effectively with the people who are already in the group. Yeah, and see whether or not like the research is what you thought it would be and is as fulfilling as you thought it would be. Yeah, so I think in undergrad, it's definitely a good time to also do that, like get a flavor of even just like what research looks like at like a fundamental level. Just like, do I like this process of trying to do research? Yeah, but I think when you get to graduate school, like within your first 2 years, you usually like specialize in some physics field or another. However, just because you specialize in a field doesn't mean there's not room to move in that field or outside of it. Yeah, so like a lot of the skills you get as a physicist are transferable to other areas of like research. Like for example, like if I'm measuring like magnetic materials in condensed matter, but like if I wanted to measure, I don't know, like materials that are used in solar cells or something, solar panels, like I could probably make that transition in not too difficult a way because a lot of the skills are very similar. Like while the physics that we're thinking about in both the systems are like totally different, there's lots of like transferable ideas and skills. Yeah, good question. I think I'll say now, you don't have to stick around any longer if you don't have any more questions, but I will stick around for maybe like 20 more minutes or so and answer questions if you have any. So thanks for coming. Yeah, hope to see you at the next U Prime Talk. I'll keep answering questions now. Yeah, Angela.
Okay, so my question is for those of us who have taken a nice little break after getting the BS, is it recommended to maybe come in at a level only searching for the master's, or should we just dive right in? Because ultimately I'd like the PhD, but I know I'm extremely rusty. It's been about 3 years since any of my physics classes.
Good question. Yeah, so I don't know. I'm going to preface this by saying I am probably not the best equipped to answer this question. Okay, that being said, if somebody else has something to say that might be more helpful, please speak up. So what I will say is that I think depending on which school you're thinking of, are you thinking of CU? Is that, if you're thinking about CU, I think the master's like requirements are like pretty similar to the PhD requirements, except without the like extended research part at the end, right? So like,
Yeah, I am considering it. And of course, I am definitely not quite your traditional student. I'm about 25 years older than the traditional grad student, so that's another consideration. So I guess I'm trying to figure out, is it worth knocking the dust off, racking my brains to try to get the PhD, or trying to be satisfied with simply a master's?
yeah. So I think if you apply to the PhD program, you can always get a master's and then leave. And that gives you the option to get the master's, right? Which is the same like dusting off your brain, like getting the physics wheels turning again. The same amount of that kind of work. But then you still it's open-ended then, whether or not you like try to join a group or not. So the research that might give you like a little bit more of the freedom to like try that if you want to, but then leave if you don't like it. Yeah, I don't know. Does anybody else have any insightful things to say?
That's okay. I know it's one of those questions that's really kind of hard to answer. Maybe something that's a little easier to answer is about the diversity. So what's the percentage of African American students? What's the percentage of female students in the graduate program for physics?
Yeah, at CU or nationally, because both those are like depressingly low numbers.
No.
Yeah.
No, but for the university there.
Yeah, I actually don't know what our numbers are, but they are abysmal, I reckon. Yeah, not good. The department like is trying to do things like CU Prime cares about this also. That's what we try to do, but yeah, they're not good.
Yeah, that's about the usual.
Yeah.
Thank you for your honesty. I appreciate it.
Yeah.
So I had a question.
Yeah.
So I was gonna ask because you mentioned towards the end of your presentation that you wrote a couple of research papers. So well, I noticed with research papers that are they geared towards a specific audience within the academic circle, or are there any research papers that are directed towards sort of a general audience? Because I noticed that they're really technical and they're a lot of the time hard to read.
Yeah. So okay, don't feel scared. Research papers are hard to read, period. No matter when you're reading them, no matter where you've gotten in your education, they are dense on purpose, and it is hard to read them. Yeah, so the papers that I like flash for a second, they're all very specialized. So like they won't really mean very much unless you like are working in the field I'm in. There are papers that are more accessible. Like a lot of journals have like either review articles or like hot topics that they'll have somebody like write a tangible like article about, and those are great jumping off points for like getting an idea of like what's going on in different fields of physics. Yeah, but like as far as like trying to read like one of the papers I linked there like right away, it's just like not worth your time probably, because it's like not, unless you're in the field I'm in, it's not super useful. Yeah.
So you're just like, your advice is like don't bother reading.
No, it's not that. It's not don't bother. I would say I think it's probably a better use of your time to like read some review articles first. Like if you have anything in physics that you think is interesting, and if not, you can go to like science.org or like nature.com, and they both have like lots of articles about like popular new like physics things. So if you have things that like you're really interested in, reading some review articles about research that's done in those fields, so just typing like, I don't know, review articles, gravitational waves, and that'll give you an idea of all of the types of new research that's going on relating to gravitational waves. And then let's say in that research article, you see like something that's like, the laser used in this thing was a blah, 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 like blah, 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 blah. And then you're like, I really think that's interesting. I'd love to know more about the laser. You can follow that up with the more specific research papers.
Okay.
Yeah.
I mean, there's like a book I got, like philosophy of physics. I only read a couple pages, but it seems pretty. It's not very technical. It's like pretty easy to read. So
nice, good.
It's pretty interesting. Yeah.
Shannon.
Yeah. So I actually just thought of like a question about like so when it comes to like grads, like what comes after the bachelor's degree. So wait, so it's like or how similar are like master's and PhD stuff? Like how does all that work?
Yeah, so I think a lot of physics grad schools, you just apply for a PhD, but sometimes they'll have like a master's degree also. So like the degree I applied for was a PhD, but you usually, if you're applying for a PhD, you can like have the ability to get a master's degree like along the way. Like it's usually multi-component, right? So like your part of your degree will be like complete these 9 courses or like take this exam, and like that part will be the part that's actually the master's degree part, and then you just continue through. Yeah, so you can apply to either. It's usually with master's degrees, it's usually more focused on like coursework, like learning like material from like books and stuff, and like usually less research focused, but some, depending on the college, some master's degrees can have like more like some research component. Yeah. Does that answer your question?
Yeah, thanks.
Cool. Katarina?
Yeah, I don't know if you are able to answer this or not, but I was just kind of wondering what type of opportunities we can expect just getting our bachelor's versus getting like a master's PhD. Like what can you do with the bachelor's if you like can you even do research if you have like a physics bachelor's or stuff like that?
Yeah, so actually I don't know how unique this experience is, but I'll just I can only speak to my experience. There was an undergraduate student working in the lab that I'm in now who stuck around for, I think, 1.5 years after they got their bachelor's and like was a research assistant in that lab. So just like conducted research, having a bachelor's degree. I also had some friends from my undergraduate in the physics program. I think, let me see, it was like 6 people, so that's not very many. One of them went to graduate school. One of them got a job in industry where they analyze like the earth underneath buildings, and then they tell engineers whether or not like it's safe to build there, which is awesome. I have like no idea how those measurements would work, but that's like really cool. Yeah, I actually don't know what the other people are doing. I think the thing that undergraduate bachelor physics people tell themselves is like that industry is an option, but I don't really know. Yeah, I never had to go that route, so I don't have a ton of experience on what kinds of jobs are available. Does anybody else have any experience in here that might be able to speak to that?
A little bit. Having your bachelor's, if you're interested, you can teach at the high school level. You can work as a lab assistant, and depending on the university, there are actually some awesome undergraduate research opportunities. So for where I came from, the best thing that I thought was that we got to work with CERN. There were only a few of us that would go every summer, but we got to work with the accelerator, and we got to work during the shutdown. We got to try to develop new modules to go in. So it's pretty awesome. It's not that many people, but there's always opportunities. You just have to keep searching. And of course, if you want to be an accelerator operator, they will take you and they will train you, but they won't pay you as much as they pay someone that has a higher degree.
Yes.
Cool. Good question. Thanks. I hope that was helpful in some way. I think the more times you ask that question as an undergraduate student, the clearer the picture. Sorry, it's not the clearest answer. Yeah. Or at least from me. Yeah. Any other questions? Doug.
Yeah, Ian, you talked about first 2 years of grad student orbiting around the labs, taking a sample of what's available. How do you go about getting into that, getting an entrance to the lab? How do you do that?
Yeah, so it's anomalous. It's like designed in a way that I very much dislike, so I won't speak kindly of it in hopes that eventually it changes. There's no like clear process like that you're told to follow. Like there's no clear process to do it other than like look at like I think what I did, I looked at all the physics professors who were doing something that I thought I might like, and then I like went and looked at some of their papers and was like, oh yeah, maybe I'd like to do this, and then I emailed that professor. I reached out and eventually got an email back, and then started like going to meetings and stuff. And I think like the process is every level of like lacking communication, from like no response to emails at all to like people being like super responsive and like reaching out to you even. So I think that happens very infrequently. However, yeah, so that process is complicated, and I think it's bad. The best thing I can tell you to do is to like email, knock on doors, like not be a nuisance, but be a nuisance kind of. Yeah, like if you want a position somewhere, just start showing up, and maybe they'll give you a job. It shouldn't be like that, right? It should be like much clearer, but yeah. I don't know. Does anybody else have experience that's not that? Tyler or Sarah?
No, I was going to say it's just a lot of getting to know people and getting people to know you. And once you make connections and start to like explore different things, then pretty soon somebody will take you in, hopefully.
Angela, yeah.
Yeah, it's pretty much the same on the undergrad level. You really have to search, like you read who's doing what research, and then you just have to bug them and pretty much be willing to do whatever grunt work they want, just so they'll talk to you at first. So whether it's stapling papers or carrying whatever, and you really have to keep bugging them. You email them, you show up at their office hours or whatever, and then you just talk to them and figure out what they're doing. And if it's something you might be interested in, and hope that they like you enough to say, come on in and take a look.
So, are you still answering questions?
Yeah, sure.
It was kind of like related to what you guys were talking about. So I realized that like how things are looking for me in terms of physics, it's pretty dry. So I was wondering, are there any like well, this is basically the only physics class I'm taking this semester, but for undergraduates, are there any sort of very like research opportunities outside of just general classrooms for undergraduates? I know that's like something that's geared more towards graduate students, but is there anything for undergraduates?
So we'll talk about it more in the semester about like what research looks like at the undergraduate level. There is research available. I think it's made exponentially harder by the fact that like the pandemic situation. It's like hard to go knock on doors and like be like learning something if you can't like go to like the lab, right? So I would say if you're like a first or second year student, that it's totally okay to not worry about trying to get research yet. Like oftentimes the further along you are in your physics degree, like the more stuff you'll know, the more knowledgeable you'll be in a lab if you're looking to do something in a lab, and the more likely a professor will be like, oh yeah, like you know how to like use an oscilloscope, like come on in or whatever. So I would say like, yes, those opportunities exist, and we'll tell you more about them throughout the semester. Don't feel bad if you don't have one yet, but if you're looking for stuff to keep you busy, like to keep you interested, or like looking for avenues to learn more and more quickly, like that's something that we can definitely talk about more. Like we can give you resources to learn quicker if you want. Yeah.
Right. So you're saying just like this is a very like natural process. Like I should just probably wait, just kind of like it's going to happen eventually. Is that what you're saying?
It won't happen unless you seek it out. I don't want to make it like it's not going to fall onto you. But I think it'll like if you wait, like it's not gonna disappear either. Like it'll only get easier if you wait longer, if that makes sense.
Okay, yeah, that makes sense.
Not saying wait until like, second semester, senior year. That's too late, I think. But also a thing that you should look out for are undergraduate research opportunities called REUs, which are things that you can do like research in totally orthogonal fields in different summers, and you go to a different university and do research there. So it's like a cool way to travel. It's a cool way to learn about science, and they're geared just for undergraduate students. So like they have some project that exists for you to come work on. Yeah.
Okay.
I highly recommend those as a way to start getting research experience.
Okay. Thank you.
Yeah.